Let's talk about something in the world of machinery that, on the surface, just doesn't seem to make any sense at all. It has to do with balancing rotating parts. Now, you'd probably think the speed you test it at should be the same speed it runs at in the real world. But, well, that's usually not how it's done, and we're going to dive into exactly why. So here's the question that kicks this all off. It feels completely backwards, right? If you know a motor is going to be screaming along at 3,000 revolutions per minute, why on earth would you test and balance it at a fraction of that speed? The answer is almost always no, you don't match the speed, and the reason why is actually pretty fascinating.
And this brings us right to what we can call the speed paradox, that gap between what our gut tells us and what the engineering actually demands. To really solve this paradox, we've got to start by getting our vocabulary straight.
You see, this whole puzzle kind of unwraps itself once we pull apart two very different concepts that, honestly, get mashed together all the time.
Okay, so let's build our foundation here. What are we actually talking about when we use the terms balancing speed versus operating speed? They are not the same thing.
First up is the balancing speed. Now, this is the speed that's used in the shop on a highly specialized machine. Its one and only job is to spin the part just fast enough for that imbalance to create a centrifugal force, a force that the machine's super-sensitive sensors can pick up loud and clear. It's like turning up the radio just enough to hear the song without any static. It's all about getting a clean, perfect measurement. And then we have the operating speed. This is the main event. This is the speed that matters in the real world, the speed the part was designed for when it's actually installed and doing its work, whether that's spinning a fan, driving a motor, whatever it is. This is where performance counts and where any vibration problems are going to make themselves known.
Okay, so we've got two different speeds for two totally different jobs, but that still doesn't answer why the balancing speed can be so much lower. The real key to this whole puzzle, it comes down to the physical makeup of the part itself, what engineers refer to as the rotor.
So what's the deciding factor? What's the one thing that determines whether you balance slow or fast? It all hinges on a single, crucial physical property of that rotor.
And here it is, laid out perfectly. On the left, we have a rigid rotor. This is going to be most of the stuff you run into. Things like pulleys, pump impellers, smaller motor parts. They're so stiff that they just don't bend or change shape, even at their top operating speed. For these guys, the imbalance is a constant. That heavy spot doesn't move or change, whether you're spinning it at 600 RPM or 3000 RPM. That means you can find it and fix it at a low, safe speed, and that fix will still be perfect at high speed. But on the right, you've got flexible rotors. Think long drive shafts, high-speed turbines. These things literally bend and warp as they speed up. This means the imbalance itself actually changes with speed. So for these, you absolutely must balance them at or very near their operating speed to fix the problem as it will actually exist in the real world. So because most of the parts out there are these rigid rotors, engineers aren't cutting corners by balancing them at low speeds. They're actually doing it that way on purpose. It's a smarter, safer, and way more efficient method to get the job done right. Let's break down why.
I mean, the practical reasons for this are huge. First and foremost, safety. An unbalanced part spinning at thousands of RPM can generate incredible forces, enough to make it fly apart. Balancing slower keeps everything under control. Second, you get better data. High speeds create air turbulence, engineers call it windage, and that can mess with the sensor readings. Slowing it down gives you a much clearer signal. And finally, it's just plain more efficient. There's less wear and tear on the expensive balancing machine, and you save a ton of time because you're not waiting for these long spin-up and braking cycles.
All right, let's pull all these threads together. We've defined the speeds, we've figured out the critical difference between the parts, and we've seen why slower is often better. Let's put it all side by side for the final showdown. This table sums it all up beautifully. Balancing speed, that happens on a special machine in the shop. Operating speed, that's in the final piece of equipment. One's purpose is to measure and fix. The other's is to do the actual job. And here's the absolute key takeaway. For the vast majority of parts, the rigid rotors, the balancing speed is just a small fraction, maybe 10 to 30% of the final operating speed. It's only for those special, high-speed, flexible rotors that you have to get those two speeds to match. And this quote just says it all, doesn't it? The mark of a quality job isn't about just spinning a part as fast as you can on a machine. That's not the goal at all. So the real takeaway here is this. The balancing speed is simply a tool. It's a means to an end. And that end is to get a smooth, vibration-free machine that works perfectly at its intended operating speed.
The paradox isn't a paradox at all once you realize you're not trying to match speeds. You're just using the right tool for the job. Thanks for tuning in.